In this example, we're going to consider the deflection of a horizontal beam. The idea is if you have a beam, usually starting off flat, define y as a positive direction downwards. When you apply a load to that beam, it will change shape. And depending on how it's supported, it may just bend in the middle, or it may bend downwards if it's only supported at one end. In any case, we're able to predict that amount of deflection using the differential equation shown here. Y is the actual position of the beam from left to right. E and I are constants that relate back to the material itself and its shape. And P of x is the load. Where are we applying a load? What magnitude is it? The units for that are newtons per meter. So how is the load distributed along the length? Our first challenge here will be to predict the shape under load of a cantilevered beam. And cantilevered means that it's attached to a wall at one end and free at the other end. And the beam we're going to study is 4 meters long, but has the load distributed in the last 3 meters at a rate or at a density of 600 newtons per meter. We have some E and I values here, though we're going to save those for the end as we work through the calculations. The fact that this is a cantilevered beam gives us these boundary conditions. At the left-hand end, we're told that y is 0. It's pinned to the wall, it doesn't move. We're also told that the slope or the angle of the beam is 0, so it's held flat. After that, it can distort. The other two conditions are the end conditions. And because this is a free end, what that boils down to is the second and third derivatives at the point at the end are 0. There's going to be no curvature and no third derivative, no distortions from that level. Before we can predict what the beam is going to look like under load, we need to express this in some more meaningful way than the diagram. And fortunately, it's fairly straightforward. Our variable, independent variable here is x, and for the first meter, there is no outside force. So this is our loading force, or loading function, p of x. On the first meter, there's nothing. On the other meters, 1 through 4, these have a load of 600 newtons per meter. And that defines our differential equation. Of course, we need to use step functions if we're going to try to solve this with Laplace transforms. And that's fairly straightforward in this case here. The left-hand side doesn't change. It's still the fourth derivative with those constants about the beam. And on the right-hand side, we're going to have 600 u1 minus u4. The idea being the force turns on at x equals 1 and turns off at x equals 4. Well, this is not too bad so far. Now we can take the Laplace transform of our differential equation. We get the EI as constants out front, and then we have s to the 4 y of s, and then we have our sequence of lower powers of s squared, s, and a constant, and they're multiplied by the increasing derivatives of y prime, and y double prime. And we need one more term, so we'll have just y triple prime at 0. So that collection of terms is what we get when we transform the fourth derivative. Now the issue is, we know two of these values already. They're 0 and 0. But these ones we don't know, so I'm going to just give them quick names here. We'll call them A and B. Remember, what we do know are those values at 4, but they don't help us right now. So we're going to have to solve for those later. Now what about the right-hand side? Well, in this case the function is nice and simple, it's constant, and the step functions then have a simple transform of e to the minus 1s over s and e to the negative 4s over s. Our next step is to simplify. We have our e times I to all times s to the 4y of s minus sa minus b, and that equals our right-hand side, which is e to the negative s over s minus e to the negative 4s over s. And then we are honing in on y of s, so we'll bring these two other terms over. So I have ei s to the 4 y of s equals sa times ei, that would be multiplied in, And we'd also have plus a b, ei, and then plus the 600 times the e to the negative s over s minus e to the negative 4s over s. And last but not least, we can simply divide both sides by this s to the 4 ei. And the same for this term. And last but not least, the same for this term here. And that gives us our transformed version of y of s. We'll continue this further on the next page. Cleaning up and canceling terms, we end up with two terms that are simply powers of s, and then these more complex terms on the far side. On the plus end of the scale, there is no partial fractions required in this particular example, so thank goodness. Everything we have here in terms of terms are ones that we can simply inverse transform by inspection. Going ahead and taking that inverse transform, the only things we have to tweak are the coefficients. If we have an s cubed on the bottom, we have to remember that's the form Sn plus 1, and we need an n factorial on top. So I'll multiply by 2 there. Likewise, we'll multiply by 6 here, 6 over 6, and these terms here will need 24s, or 4 factorials, to work themselves out correctly. And that gives us y of x, which will be the deflection in this beam. In this term, we're going to get the 2 over s cubed goes together. So we have an a over 2 times t squared. Oh wait, no, this time it's x as our independent variable for this problem. Then we end up with b over 6 x cubed plus a 600 over e times I. And these ones are a little more exotic. We have 1 over 24. And we have a combination. We have the exponential, which means we have a step function, u sub 1. And we ordinarily would have t to the 4. But now, because it's accompanied by that exponential, we have t minus 1 to the power of 4. For the second term, notice that the exponential is a 4. So we're going to have negative 1 over 24. That comes from this part, and grouping the coefficients together. We're going to have a u sub 4, and then a t minus 4 to the power of, well, we have an s to the 5 in the bottom. That means the transform function was t to the power 4, and we're going to change those to x's. Automatic pilot's a terrible thing sometimes. And that is our inverse transform. And we see that it has the same kind of structure we would expect from the differential equation. We get simple powers of x, sometimes shifted, but that's fine. There is a little bit of extra work still left to do because we need to solve for a and b. But fundamentally right now, we know that the shape of this beam under load is going to be defined by some fourth order polynomial. Notice though it's going to change at 2 points. We're going to have this basic function here, and then at x equals 1, we're going to activate this function, and this one here is going to get activated at x equals 4. That's a little less interesting because that's actually the end of our beam, so we might be able to skip that completely. The main part of our function will be this down to the start with the a and the b terms. To find a and b, what we're going to need to do is use our other conditions that we haven't used yet, and those are the second derivative of y at 4 is 0, and the third derivative of y at 4 is also 0. And those capture the idea that this is a free end for the beam. It can move up and down, so there's no condition on y itself at 4, but it's not going to be bent at the end, and a similar condition applies to the third derivative there. It's going to help us if we have our function written in piecewise form, because then we can actually see which functions apply at x equals 4. When we talk about the first interval, the only functions that are on are these leading two terms. They don't have any step functions associated, so they just happen to be in the function. And that's what we'll get when 0 is less than x is less than 1. Once we reach x equals 1, then we have all the previous terms still on. They never turn off in the way we're modeling these systems or representing them with step functions. And then we have the 600 over 24. That's better known as 25. times x minus 1 to the power 4. And that's between 1 and 4. And you'll notice we don't need this last point here because the beam ends at 4, and so something turning on at 4 has no real effect. The function's continuous. If we went out and had a 5 meter long beam, we would need this, but here we can skip over it. Also notice that there's no u's in the piecewise format because it's implicit. When we reach 1, this function gets turned on, whereas when we wrote the function as one line, we needed an expression, or a function in this case, to represent that transition, that turning on at some moment. Piecewise, we don't need those anymore. Now, we can use this last function here to evaluate y at 4, and in particular, the second and third derivatives, so we can solve for a and b. So on this interval, x equals 1 to 4, so this part of the beam, we have the shape of the beam defined by this formula, and what we need are y double prime and y triple prime, so we're just going to take derivatives to get to that. We're going to take x derivatives, and that'll give us y prime is 2ax. We have a 2 in the bottom, so it's just ax. Then we have 3bx squared over 6. That's better known as a half. And then we have 100 ei's x minus 1 cubed. Now we need the second derivative, so we simply get a, the 2 and the 2 here cancel, we end up with bx, and we end up with 300 over ei x minus 1 squared. And the third derivative is simply going to be b plus 600 over ei x minus 1. Now we sub in x equals 4 and y double prime equals 0. That's our boundary condition at the end here. That'll give us a plus 4b plus 300 over ei times 4 minus 1 squared equals 0. And in the same vein down here, we're going to plug in x equals 4 and the third derivative equals 0. And that's going to give us b plus 600 over ei times 4 minus 1 equals 0. This equation here is definitely the simpler of the two. 600 times 3 is going to be 1800. It's going to be on the other side of the equation, so we'll have 1800 ei. And then when we sub that into here, we're going to solve, and by the time we're done, it'll take a little bit of calculation, but we'll get that a is 4500 over ei. 1 and 2. And so our deformation of our beam, the shape of this beam when we apply that load, is going to be defined by, going back to our original function, here it was in piecewise form, the a went with x squared, b with x cubed, but it was a over 2 and b over 6 everywhere we saw it. So if a is over 2, we'll have 2250 over ei x squareds. B over 6 is 300 over ei x cubed. And then that was it for the interval 0 less than x less than 1. And then we duplicated that on the second interval, the only change being the addition of the third term, 25 over ei x minus 1 to the 4. And that applies for 1 less than x less than 4 to the end of the beam. And that is our completely worked out formula for the shape of the beam under this load. So quite a lot of physics and math to lead up to this kind of solution.